Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right.
Did you see
everybody.
how smooth that was?
That was a great transition.
I was so every time I'm at this point where I'm like, it's either like 5 seconds or 3 seconds. I have to click and change it, and it's like professional broadcast, like we're making a movie, you know, where it should just be like whoosh, whoosh, and then it comes up to us.
Yeah.
So I mean, but it's coming from your face to your face.
Well, yeah, that's true. Well, our face.
But it's your face to our face.
To our face. Yeah. I think
it's not my face to I don't even exist in the first 6 minutes. I'm absent. I don't need to exist either, which is fine. But it's, you know, it's definitely the transition smoothing between the intro and whatever is like, it's an art form.
Yeah. Oh yeah.
It takes practice.
You're doing a great job.
Oh, thank you.
Doing a great job. And you know, it was funny right before we started this live stream. Just, you know, we were talking about, you know, self-confidence and doing rest. And you know what? You are you, and no one else can be you. And if you feel bad about electrochemistry or not doing great in electrochemistry, you should compare yourself to people like Michael Faraday, because they were so much better. No, I'm just joking.
No, you should compare yourself to you 12 years ago before you even knew that electrochemistry was a word. So even if you don't think you're good at it, you now know that electrochemistry is a word, and that is better than you were yourself a decade ago.
That's right.
That's something. You're not Michael Faraday level, but you are you level, and that's good enough.
Yeah, that's right.
There's your motivational speech for the day, and that was just terrible, but I don't regret anything. Welcome everybody. We're happy to have you here. You can ask anything you want about electrochemistry and type it into the chat. We do have a question from Apurva, and we have a few that I want to get to that have been saved for probably 6 or 7 years. I'm going to try to get to them because we always have so many questions, and sometimes it's hard to get to the cataloged things. But first, Apurva has asked why the LSVs are recorded at slower scan rates like 1 or 5 millivolts per second during HER or OER. So one of the reasons that you might do something like that is because you're probably trying to make a TAFL plot. Is my guess. I'm not going there. Okay, I know what you're thinking.
I think like we already talking about TAFL plots.
Already ask us anything about TAFL plots. So one of the reasons why, whether it is a OER and HER, or it's LSV or CV, it doesn't, whatever. If you're sweeping the voltage and you're studying something and you're sweeping slowly, one of the reasons to do that is because you minimize basically non-Faradaic responses. The capacitance is directly proportionate to the scan rate. Did I say that right? The current is proportional to the current is and so basically the background current that you're going to get from capacitive effects, like the electrical double layer, is going to be minimized by scanning slowly, which means that the bulk of the current you measure in that case can be basically, with some amount of error, I suppose, but attributed to the process of interest, which is like largely kinetic Faradaic current associated with HER. So if you scan very, very quickly, you go the other way. And so you would maximize, let's say, or increase the amount of current response from non-Faradaic processes. And if you're trying to study OER, HER, or whatever else, you know, you would prefer to have as much of the current, which is the rate, like the rate of the reaction that, you know, driving whatever, be associated with that reaction of interest as much as possible.
Yeah. That's exactly right.
Yeah. Okay.
Yeah, we can get to
it's the magical time we can get to something. Let's get to this. Was a question on our YouTube channel. I did type in a response to I guess Aben Phillip 9779. And I just wanted to kind of chat through it because it's kind of an interesting one. It's something I thought was kind of a nice thing to talk through as far as a bit of a distinction. So the question was, which geometry of electrode, and the examples were like planar or porous or something like that, favors the fastest diffusion. Okay. And so I'll just start, and I want to hand it to you, Alex.
Sure.
You can kind of take it forward. But basically, the first quick distinction I want to make is that the speed of the diffusion is you can decouple that from things like the rate of the reaction or the electrochemical response more broadly, or other sorts of things like the diffusion layer thickness or the morphology of your electrode. But strictly speaking, to the like exact wording of your question, the speed of the diffusion is captured by the diffusion coefficient. So the diffusion coefficient has units of like centimeters squared per second or area per time. And so that defines the amount of area like a plane is moving, like a particle, a plane of particles is moving per unit time. That's like a speed. Like it's like a the speed of molecules moving. That diffusion coefficient is a property of the fluid. So it's things like the viscosity of the fluid, the temperature, what any other fluid, probably other fluid properties like, whatever. And so all things being equal, two different electrodes, but the same fluid at the same temperature with the same properties, same electrolyte. Technically speaking, the speed of diffusion is the same. Doesn't matter what the geometry of the electrode is. However, again, that doesn't mean that you would expect all of the other things to be the same. Right. Again, you can sort of think about the availability of the surface being porous or not porous or whatever. So I don't know. I just kind of start there.
Yeah. One thing that's interesting about this question, which can lead to a little bit of confusion, is that most of the time when people talk about the geometry of the electrode, they're talking about like the shape of the electrode. Is the electrode a planar disc? That's just very common. Is it a big disc? Is it a small disc? Is it like a sphere? Is it a square? Because the geometry of the electrode itself will govern the kind of response that you'll get depending on the diffusion, sort of say. So like when you have a big planar disc, most of your current response associated with diffusion is from planar diffusion, and it has less to do with what we call radial diffusion, which is the molecules coming in from the side. It makes up a much smaller fraction of the current response, if you will. And so when you talked about like, hey, which geometry of an electrode, planar or porous, well, you can have a planar and porous electrode. So porosity is not necessarily a geometry. We wouldn't use that word to describe the geometry of an electrode. We would just use that word to describe whether there are pores inside the electrode that allows a molecule to move or flow through. And so Neil's right. The diffusion coefficient is a function of the fluid dynamics of the molecule, as well, of the electrolyte, the solution, the molecule as well. If you have big bulky molecules, they tend to diffuse around slower. And so whether it's in solution, but then if it's diffusing through a membrane or through a porous structure, then it might take longer for the molecule to kind of get through. And when we think about diffusion, we're thinking about concentration. So it's not that the molecule, which is, a nanometer big or less, has a hard time moving through a 10 nanometer pore. It's that the concentration of that species slows down, if you will, or isn't completely, you'll get a concentration gradient, if you will, as you move through the pore. So hopefully that kind of clarifies a little bit about diffusion, the geometry of the electrode, things like that. When you have I guess one last thing is when you have very small electrodes, like micron-sized electrodes, you actually get a different response in your cyclic voltammogram. You'll get an S-shaped voltammogram as opposed to a duck-shaped voltammogram. Yeah. And that has to do with diffusion. That's completely a diffusion geometry related issue.
Yeah, exactly. I think it was just an interesting question because it made me realize about making that clarification of the distinction between the speed of the molecules moving and all that other stuff that you just talked about, right? All the differences of the morphology and what it does, but strictly speaking, the speed is dependent on obviously on the fluid properties, as I said. So, okay, let's see. We have a new couple questions here, and then I want to get to this thing about DRT. But let's see what Tamogna has a couple questions. So, hi, good evening, guys. Thanks for another wonderful session. Sorry, I lost that. There it is. Okay.
Oh, yeah.
So, I am trying to get RP from LSV of an aluminum sample. I'm scanning between plus or minus 10 millivolts of the Ecorr, and I'm plotting V versus I, and the slope is RP. That sounds fine. I'm using 1 millivolt per second. Is that too fast? Should I go slower to like 0.125? In my experience, 1 millivolt per second should be your upper limit. It isn't necessarily too fast, but I would recommend going slower if you can. The slower that you go, the better off it will be, for the same reason I just discussed, 10 minutes ago when I was answering a question about slow scan rates for, OER, HER, is that especially with the RP around a corrosion kind of experiment, we call this linear polarization resistance. And we really want to, minimize those kinds of non-Faraday capacitive effects on the current, right? And so typically the scan rates are usually between 0.1 or 0.5 millivolts per second. Plus or minus 10 millivolts is a good range. It's not too wide, such that doing like 0.1 millivolts per second or 0.2, 0.4, whatever, something in that range is like excruciating. It's excruciating if you do so slow, right? That's one of the reasons to, if your time is worth anything, and if you're a graduate student, and in some cases, I know your advisors don't particularly think your time means anything. So just saying it like it is here, but at the same time, right? Of course, if it's going to take like 35 hours for you to scan somewhere, it's a bit much. That being said, between 15 and 20 total millivolts of movement, you figure 10x, right? 0.1 millivolts per second. It's like, what's 150 seconds? I mean, the whole thing's going to take 2-3 minutes. It's not that big a deal, is my point. So yeah, I do think that scanning really slowly. Now, the one thing that I will say as well is that there is another thing to be considered here. Just something that maybe you might not know or think about. And it's something that we're more aware of as a company that makes the equipment and the software, and that runs these kinds of experiments. Let me try to draw and illustrate what I mean while I discuss this concept.
Yeah.
When you scan that slowly, okay, let me back up. When you do any kind of a scan, right, a cyclic voltammetry or a linear sweep, it doesn't matter what the voltage range is over time, right? Okay, we think of it sort of commonly like, we scan up and then maybe we scan back. It doesn't matter whether we go back or forth. Okay, that is not actually what's happening. I mean, just realistically, that isn't there. This is very digital. An analog sweep can kind of almost approximate this, but really what we have, if we were to zoom way in, right, is it's a ton of tiny staircases. That's actually what's happening, right? Now there's analog to digital and conversions that are happening. And so what you see on the screen just appears to be a very smooth kind of a thing. But the reality, just sort of is that the potentiostat's actually kind of making a bunch of small steps. Okay. When you sweep and you go slower and slower. Now, I don't know precisely. Of course, it probably depends on the instrument. It probably depends on some other kinds of factors that I don't know how I could answer that for every manufacturer. It'd be hard enough to answer even with our own companies, because these kinds of limits are difficult to interrogate exactly what they are. But what I mean is, when you scan slower and slower and slower, you can imagine that when I'm scanning fast, it's like it's going really, really fast, and it's not spending very much time at any one of these potentials. It's going quickly, and it basically is pretty smooth. But if you're going really slow, it's like step, and then it's waiting, and then a step, and then it's waiting, and then it's step, and then it's wait. Like, because there's so much time associated with the scan over a short range of potentials, this kind of process is not always ideal from the potentiostat and the code perspective. What it's not doing for you well is averaging out points at each step. What the typical process for a potentiostat is that what it's actually doing, and it's very, very fast usually, right? Because as I said, when you're sweeping fast, is that it steps up the potential and then holds it there for some period of time. Now it's probably microseconds or milliseconds or something. And as it stays there, there's a current response, right? And the current technically decays or goes up or down or whatever. And then it basically gathers the last point, and that's like the E and the I, whatever. And then it steps the potential up a tiny bit. And then the current, it takes a point towards the end, probably, or maybe in the middle or whatever. The point is that's how it gets your cyclic voltammogram. And then there's a bunch of E and I, and that's what it is. Now, this is all happening so fast. It's like you don't notice the steps happening there because they're so fast. It's like, it doesn't really matter in practically. But when you start scanning really, really slowly, it can matter. And so what actually is a procedure is called linear polarization resistance. It's actually exactly what you're talking about, except that typically the potentiostat in the software does not do it the way a CV or an LSV does. It actually acts like a lot of individual chronoamperometry steps. So the reality is it might actually look, if you were to zoom way in a similar way, where there's a bunch of it's a bunch of steps, stepping up the voltage and waiting in time, except that a lot of times what it's doing is let's just make this like the current, corresponding current axis. And it's like at this one, it's like there's a bunch of points, and then it steps up and there's a bunch of points, and then it steps up and there's a bunch of points. And don't forget about the, maybe this won't look so noisy. Maybe it decays up this way. Maybe it decays down this way. But the point is the program can kind of average here, or maybe average the last 50% or something. But there's programmatically, your accuracy of a very slow sweep will be better if you basically take a bunch of discrete steps and you average some portion of the data. And that is what an LPR experiment actually does more properly. And that not only allows you to accomplish the slow sweep, getting a better isolation of the kinetic, kind of information, as minimizing the non-Faradaic electrical double layer contributions, but it also allows you to get a better, like almost like signal to noise at each discrete step. And it allows you to, in some software, like my company's software allows you to do this. Some do. I'm not sure if all potentiostat manufacturers allow you to, but you can set the step size. So like if you want to do it like every 0.1 millivolt and do 1 millivolt per second, 1 second, and then 1 second, and then 1 second, like that. But it's like you could also do like every like third of a second, it moves up a third, 0.003 millivolt. You have control over those in some software platforms, basically. And so it just allows you a little more control to be able to average out some of the noise and get a more accurate measurement of that really slow sweep. So that's just something I wanted to mention, that just be aware if you're doing literally linear sweep voltammetry or cyclic voltammetry for your RP setting in your potentiostat, it might not be the best method to be doing that slow of a scan rate. But again, just to reiterate, the last thing I'll say is that generally speaking, I would not go any faster than 1 millivolt per second. And very often slower scan rates are used for that kind of measurement.
All right. Very good. We have a follow-up from Tamogna. He's just asking, should RP change by scan rate? I think ideally no.
Yeah, ideally no. And the reason is that if you scan slow enough, you are going to be taking out those effects from, things like electrical double layer and things of that nature. Eventually, if you scan fast enough, you will start having it change. You could do this. I think most probably what you would find is one of two things. Like, for example, if you wanted to like do a sort of proof of concept test for yourself, and again, hopefully you have like an LPR experiment or some sort of averaging experiment like I just described, and not CV or LSV, but if that's all you have, maybe that's all you can work with. But do it at 0.1, 0.2, 0.4, 0.6, 0.81, millivolt per second. Do like 3 or 4 or 5 or 10 different scans at different scan rates. See what the RP looks like.
Mm-hmm.
Is it changing? If it's changing in a very like linear or predictable way, it probably means one of two things. It's the sweep thing I just talked about being a problem, not being the best method for this, the sort of not averaging properly or what have you. Or it just means that you are, still having impact from this non-Faradaic kind of thing, because, the current is proportionate to the scan rate as a result of the capacitance. And so, you want to scan slow enough so that those are minimized. What I suspect you would find, if I were doing it, what I would hope to find is that RP would be a little bit different every time. Like, there'd be some measurement error, like this just normal. You're never going to get exactly the same value, but it would be somewhat random. That would be a good sign to me, because that just means like, okay, well, there's a little bit of measurement error. It's just, this is electrochemistry, but it's sort of like it goes up and then it goes down and it goes up and it goes down, and maybe it's roughly the same. That would be a good sign to me, because then you could actually do it. If you felt so inclined, you could do like 3 or 4 and average the RP and say this is a aggregate, average value, and that's reasonable. Be a reasonable way of obtaining it as well. So that's what I would have to say about that. But do the test yourself and see what you find. I think that would be a good instructive thing to observe.
Yeah. So we have a question from Sidhu. Sidhu is asking, good evening, how to decrease the OCP, the open circuit potential, for a mediated bioanode. It's using Prussian blue and glucose oxidase, which gives an OCP of 0.1 volts. It says need negative OCP. So there are a couple things. So one is, why do you need to have a negative OCP? So the open circuit potential is, in a way, just the open circuit potential. It is, the difference between the electrode potential and the solution potential, and then that's even measured against a reference electrode. And to a degree, it almost doesn't matter that much, and I'll explain why. There's a simple way, if you will, to make your open circuit potential negative. So I'm actually going to share with you. This is on our website. This is the Pine Research website. If you go to tools, you can go to reference electrode calculator. And all I'm going to do here is I'm just going to type in 100 millivolts. And then I'm going to select a reference electrode. Let's just say I'm just going to pick this calomel electrode. I'm going to calculate it. And what it'll do is it's actually telling me what this 100 millivolts would be versus a variety of different reference electrodes. And you can see, if I actually switched from my calomel to this mercury sulfate electrode instead, I can actually get to, around minus 200 or so millivolts. So I started with something that was 100 millivolts, and by changing the reference electrode I was using, I can now make it, negative. I can now have a negative open circuit potential. So that is, in a way, this is answering your question. This is how you can do it. You just have to pick a different reference electrode. But I think that also goes to kind of the point of like, why do you need to make it negative? Because by changing something that's not your electrochemical system, I'm able to change what my open circuit potential is. I just changed what my reference electrode was. So that's how you would do it. That's a way. Of course, if you wanted to mess around with Prussian blue and glucose oxidase and electrolyte concentrations, you can do stuff like that. But changing the reference electrode will adjust the open circuit potential based on how it's measured. So, Sidhu, let me know if you have any further questions about that or clarification. If you're trying to figure out, okay, well, I think changing my reference electrode is the way to do it. Which one to use? Try using that reference electrode calculator on the Pine Research website. Okay. Do you want to go to the next question before?
Yeah, and then I'm going to do the.
Then you're going to go
thing,
into
unless there's 6 other questions.
Yeah,
anytime.
yeah,
But,
which can happen.
Yeah, it does happen. So our sheet says, "Good evening. What can be the best method to remove bubbles in hydrogen evolution reaction repeated for many cycles of LSV?" Yeah, this is a good question, and honestly, it's something that it's one of these like, what do you do with HER, OER experiments? It's a real problem. So one of the strategies is to rotate an electrode. If you rotate, sometimes that kicks bubbles away. You're spinning the electrode. You're spinning the solution's whipping around. A lot of times when a bubble forms, it kind of whips away very quickly. If you don't have a rotator, one of the strategies that people do is that if you have your electrode in solution, put it at an angle so that when the bubbles come, there's place for them to escape. If the electrode's like straight down, the bubble sits there. It doesn't have anywhere to go. But if it's at an angle, well, then gravity sort of allows buoyancy, whatever, allows the bubble to escape. That's one way to do it. So getting your electrodes, and that's not always easy, right? Because cells sometimes they're at an angle, but sometimes they're straight down, and you have to sort of engineer a solution sometimes. So that can be tricky, but yeah, I other than that, I mean, a lot of times it's like, especially if you're letting it run automatically, you're not, sometimes if you're watching it, you can kind of like, it's not ideal because you'll disturb the electrochemical data. But like if you see a bubble, you give like a flick.
Yeah.
I've seen people do like they flick the electrode literally, or shake it a little, which is then your data looks all messy for a minute. But hopefully it's not in the HER region. Like you scan negatively, you do HER, you scan back. When you scan back, it's like shake it, get all the bubbles away, and before it goes back, or like so there's all kinds of these methods. It is sort of one of these unfortunate things, as I do mention from time to time. It's like electrochemistry being mostly a solution phase kind of a experiment, right? When you do something that generates gas, you just have a naturally difficult situation because gas breaks up the electrode electrolyte interface in solution. So try some of those things that I mentioned. They might help you sort of divert the bubbles away, so to speak. But otherwise, it's like part of the fun. It's part of the challenge. It just is. I wish there was like one super easy, tried and true method. I think this is like one of the more common things that folks studying hydrogen evolution or oxygen evolution reactions have to suffer through, unfortunately. It just kind of is, for sure. Okay, before let me I'm going to get to this DRT thing. So I'm going to kind of dive into this a little bit. So this was from, I actually don't have who it was from. It was someone who had emailed with you.
I know.
I don't know if I know who it is. That's okay. It'll be instructive, I think, anyway, because this person had some impedance data and then a few questions about DRT. So let me share. There's just a short sort of couple of PowerPoint slides, and I'll just share this and just talk through it a little bit. So this person who had some impedance data. So I don't know the full details. You had talked with them, Alex, I think, and so I don't have.
This is basically what they shared with me.
Okay, so what I know is what you know, which is what I'm looking at. But okay, So effectively, they have this cell where there's, I guess it's probably a battery, so lithium iron phosphate, and then they have ECD. Yeah, it's obviously a battery. So they had to use the silicon as their anode. It's a battery cell. They did potentiostatic impedance here. Definitely a battery because they only went to 100 kilohertz down to 10 millihertz, amplitude of 10 millivolts. And they used DRT. So DRT stands for distribution of relaxation times. And so some of my answer here will be, I guess, taking for granted what that is. So if you need more explanation about distribution of relaxation times, anybody who's watching this, I can explain that if necessary, but I'll sort of move forward under the assumption that that you know what DRT is, I guess very generally. Okay. Okay. So this apparently was their data. So they had kind of what looks like a Randall circuit almost, semicircle, and then either some Warburg or some, I guess, higher impedance sort of secondary process. Sometimes that happens with the cathode and the diffusion kind of melt together with a battery. Sometimes you get a bit of this low frequency wide semicircle that's a mix of diffusion and some other things. But in any case, they interpreted it mostly as diffusion, but they had a few queries specifically regarding the DRT. So the first one was that since the DRT method is not applicable in the Warburg region due to divergence from the real axis, how can I identify the onset of the Warburg region in order to exclude that data before performing DRT? So just to clarify, you are correct. It is inappropriate to use DRT analysis where you have either purely capacitive or mostly capacitive, purely or mostly inductive, or purely or mostly Warburg diffusional kinds of behaviors, I guess. And so it isn't a perfect answer, but basically, if you notice especially on the Nyquist plot, right, where it's really starting to go up at a 45-ish degree angle, it's definitely subjective for sure. But I mean, I would not let my DRT analysis be done much beyond where the points start escaping, if you will, or something like that. Now, the tricky part, of course, is that you could miss a time constant, right? That's, let's say at the beginning of where it looks like Warburg. The problem is you're going to have diminishing returns very quickly as you allow yourself to probe into the points that are quickly increasing up the y-axis. DRT is fundamentally a transformation of impedance data that relies on the assumption of RC elements, which is how you have time constants, a distribution of relaxation times. It's an assumption of a bunch of time constants, which are RCs. And so data that's pure diffusion or capacitive or with a high imaginary impedance moving away from the real axis does not fit that description definitionally. So you want to cut it. So basically you need semicircles, right? You need mostly semicircles that finish. And you can even see that it looks like what this person did. They basically did the full data and then they removed some. And it's like what you're seeing here are some peaks and they're getting bigger and bigger over here on the right. And it's like, okay, well, there's one peak here at like 10 to the minus, 2 minus 1. And there's another peak, it's a little bigger. Another peak, it's like, well, which one of these is real? Which one of these is not? It's like, honestly, it's really hard to tell because if you keep going, you'll just keep getting larger and larger and larger peaks. And presumably if they went even lower in frequency, they would just continue to get more peaks. And it's like, where do you cut it off? Which I get is the point of the question, but it's like, I wouldn't want to go almost anywhere into the Warburg region because you're going to possibly be drawing false conclusions about charge transfer processes that are not there. So I would prefer, generally speaking, to be pretty strict about my interpretation of the DRT, which is to say, if as soon as it starts increasing on the y-axis, cut it off pretty quickly. So that's my impression.
Mm-hmm.
Second question here: is it necessary to extrapolate the experimental impedance so that it converges towards the real axis before applying DRT? Yes and no, right? It's similar to what I just mentioned, where if the data are not close to the real axis, DRT isn't really appropriate to use. But if it's something where like the left part of your Nyquist plot or something like that is like you didn't go to a high enough frequency and you have something like this, and it's like, oh, do I have to like extrapolate this data? It's like, not really. You might get something that's like on your DRT, you might kind of get like not a perfect looking peak or something like that, but or maybe but I guess what I would say is it's similar to circuit fitting. Like circuit fitting can help helps extrapolate that kind of thing, and it's just, it varies. Like if your peak is like, if you have like this much of a peak, it's not going to be too accurate. If you have this much of a peak, it might be a little more accurate. If you have this much of a peak of a semicircle, if you have this much, it's like, okay, it's almost okay, well then obviously it's a perfect semicircle. It's like it's a sliding scale. It's hard to perfectly answer that question, right? Generally speaking, circuit fitting or DRT, provided it meets the criteria I just talked about, like it doesn't have to fully form perfectly looking semicircles. That's what DRT is for, because this is an example. You have one semicircle. Well, is it actually like, two charge transfer processes or just one? Well, that's what DRT is good for. It'll help you kind of deconvolute that. But if your semicircle is more than halfway complete, let's just say, for example, probably it's going to be okay, and you don't necessarily need to extrapolate. But the way to extrapolate is to redo the experiment with a more complete frequency range, hopefully, and then hopefully some of those peaks would resolve. But I wouldn't recommend extrapolating it and like fabricating the data, because if that's what you mean by extrapolate, it's like that's not really appropriate. Like that, you don't have those data. You're making up impedance data that you actually didn't collect, and I wouldn't necessarily recommend that. It's one thing to do it circuit fitting. It's another to like add points or delete raw data. That's not really ethical, right? I wouldn't recommend doing that. All right, just two more questions of this DRT discussion. So how can impedance values corresponding to processes like charge transfer and SEI formation be extracted from DRT results? Is the impedance determined by area under each DRT peak? So yes, that one I had to read about a little bit just to confirm. I wasn't sure, but when you have your DRT, and this is, I think it's like modulus, it's like this symbol or something like that, and then that looks like the planet Saturn. Probably should go this way. Now it's a weird symbol, and I don't regret it. It's just weird. Okay,
it's all good.
Yeah, and then it's like tau down here, right? So yes, let's say you have your first peak here for SEI, and then you have another peak for I don't know, whatever, charge transfer resistance. Yes, the area under the curve correlates with the impedance. Now, it's not, to my knowledge, like the unit doesn't, I don't think it's ohms necessarily. Like this is time, and this is I forget the unit, honestly. I think it might be unitless. I'm not positive. But it is, the area under the DRT curves does correlate with the relative impedance of those processes. So that is a thing. So if you have like a small DRT peak that kind of shows up unexpectedly, it's like, well, there's some other process, but its impedance is relatively low. And so you could say like, well, it's a extra process, but it's not impactful or something like that. So that is a thing for sure. What's tricky is that when you have multiple peaks, for instance, and they are like, if they mesh together, it's like, okay, well, do I take the peak, do they overlap, or do I draw a straight line down and like do this area and then this area? That to me is not clear perfectly. I don't know. But generally, I would sort of assume you'd do a Gaussian, so you'd sort of they would overlap, and that, the areas, you'd take like a perfect Gaussian sort of curve and get that area. Anyway, that's just my impression. But the areas do correlate with the impedance, they do. And so you can draw conclusions, which leads to the final question here that I'll answer. Says that the SEI typically appears in the short time constant region that tracks. It's usually at higher frequency and lower impedance. However, when I integrate the area under that peak, it results in a very small value, suggesting low SEI resistance, which doesn't align with the SEI resistance values obtained from EIS fitting. How should this discrepancy be interpreted? So there's a couple of things I would say. First is check just what I talked about in this last bit, like you're integrating under the curve, but like make sure you know where your limits are. If that peak is like influenced by other peaks that are nearby your SEI peak, like how clear is it so that your integration is accurate? Number two, remember, it's more of a relative thing. It's not like, I don't believe that the area under the curve is the impedance precisely. I could be wrong, but I don't believe that's exactly the case. It's more of a relative thing. Now maybe the resistance of the SEI compared to the charge transfer resistance is not in the order that you would expect or something like that. If you are still finding a discrepancy there, my impression would be to lean more on the EIS fitting results. And the reason is that it's really directly fitting, assuming you've picked the correct circuit, the data your impedance response. Whereas the DRT is I mean, it's like Kramer's Kronig in that it's a manipulation of the data, making this sort of assumption that's not reality. It's more of identifying the number of charge transfer processes, or just processes in general, by how many peaks there are, and then that sort of secondary benefit of like getting the area to get roughly the relative amounts of impedance for those processes. But I would still use the values of the impedance I got from my circuit fitting. That's fitting the actual data, and then the width of the semicircle on the Nyquist plot is the resistance. That's the impedance. Like that. Those are the things that are more meaningful from a interpretation and in a quantifying way, in my impression. So to the last point there, and it would probably take me seeing some of the data, I guess, to really understand, why does this look like this compared to that. I would be able to answer that a little better if I saw the specific data there. Although I guess I'm not sure if it's this specific one or it was a different one. In this PowerPoint, there's a bunch of peaks in the DRT. I'm not sure which one this person was attributing exactly to the SEI and which one to whatever, because I do see a small peak with the SEI and it looks appropriate to me anyway. But so anyway, that's what I would say to that. And thank you for those questions, whoever that person was. But
I know we have the email. Just like
it's fine.
We're supposed to answer it like last week. We always get inundated with a lot of questions, so we're glad to do that. There's a question from Tamil that came up. He says, hello, I have some basic question that what is diffusion, and explain from reference. So we can talk about what diffusion is. I don't know what you mean by explain from reference. There are plenty of books that do talk about diffusion. Diffusion isn't even strictly an electrochemical thing, but it ends up being something that shows up even in biology and just chemistry. But diffusion is a mode of mass transport. So let me show you this equation here. This complicated looking equation is the Nernst-Planck relationship. It describes the flux here, which is Ji, as a function of x, which is distance or position, and it really just describes transport. How does something get from point A to point B? How do things move? And there are many different contributing factors. There's convection and migration, but diffusion is this part right here, this green section that I've highlighted. And I've kind of the best way I like to describe diffusion is it is the random motion of molecules. And that's to say that molecules can move due to the presence of an electric field. It can due to convection, the physical mechanical moving of molecules. But this one is just what I call random motion. And diffusion is defined by this diffusion coefficient and this differential equation, the change in the concentration as a function of position, x. So I have a different view on diffusion. A lot of people say that diffusion is the movement of molecules due to concentration gradients, and that's because diffusion suggests, based on this equation, that if you have a change in the concentration as a function of position, you will get movement of those molecules from one place to another. I don't disagree with it, but my point of view is that diffusion is always happening, that molecules are always moving around somewhat randomly. And so when we think about diffusion from an electrochemistry context, we're talking about molecules just kind of randomly moving around. And just because there are, different molecules over on another side, it doesn't force those molecules to move from one place to another. They would naturally just kind of randomly make their way from point A to point B, kind of directionless and random. So it is there are many models of diffusion. A random walk is, a linear random walk is one where, a molecule starts in one position and then it moves this way and that way and just moves by one. And on average, it ends up being in the same place, but all in all, it ends up being having traveled a tremendous distance. And that's how diffusion kind of works in reality. Things randomly move, but they end up going to all these different places. They get from one part of a beaker to another part of a beaker.
It's kind of a chicken and egg thing, right?
Mm-hmm.
When you think about it, it's like there's diffusion, which is the random movement of stuff, and there's a concentration gradient, which is when there's more of some crap on some side than the other side.
Yeah.
Right. And it's a chicken and egg thing. Did more of a thing happen on one side than the other side because things were moving, or did things just move and then cause that? Right. It's like which caused the other. And I this took. I feel like it's a hard thing to wrap your head around, maybe, and people seem to like, get jumping at the accusation that like the concentration gradient doesn't cause diffuse. When you say something like that, right?
Yeah.
And it's like, if you have more of your molecule over here than over here, yes, over time it will diffuse over to the other side and equilibrate like that. Like if you have a glass of water and you drop a drop of food coloring over here, blue food coloring, right? We know what will happen. That where you drop it is very, very blue, and if you just let it sit there, it will eventually make the whole thing light blue. And it will because there's a ton of blue over here and there's none of it over here. The question is the blue molecules, particles that are causing it, are they moving from here to here because they looked around and they were like, oh, over there's so lonely.
Yeah.
There's whether it's a passionate thought about that or it's just random, molecules, obviously they don't have brains, they're not thinking that way, but like, exactly. Is it moving because there's none over there, or it's the randomness of moving? And so if you just take the probability of a block of the water that has all blue molecules, they can move left or right, up or down, but the randomness of that happening is going to result in a bunch of them being over here because they're all over here. Whereas in this spot of the glass, there's none of it. So the randomness results in nothing. And just when you just propagate that randomness, they will work their way out that way. That's just what happens. And in an electrochemistry context, we end up with this gradient a lot of the times because we are reacting away some of it. We're doing a redox reaction. And so some of our molecule A over here is at the electrode surface and it's getting used up and reacted and it's gone. And so more of the A diffuses towards the surface of the electrode. But is it happening because it just saw that its friends left and it wants to fill the space? No, it just happens randomly. Mm-hmm. But so it is they're intricately tied, right? And we often talk about it as a driving force. And in some sense, that's kind of true. It's like there's a driving force that there's higher concentration over here, and so it's in some real sense, it's a driving force that it causes over here. But like mechanistically, it's just random movement. Diffusion is definitionally random movement. Yeah. So that I like that distinction a lot, actually, despite some of our friends and colleagues not being on board with us. I'm with you on that one. I actually think that's correct. It's just definitionally correct.
Yeah.
Even if you're like, no, it's the concentration gradient. It's like, fine, whatever you want to, however you want to think about it. It's not wrong.
Yeah.
To take it and say, well, there's a concentration gradient, so things are going to move this way. Fine. Mm-hmm. It's just the word because in there is not.
Yeah,
I don't find
it's
that
a weird semantic argument that I end up having with people.
Yeah. But this person asked, so we get.
But yeah, this person asked, so we talked. So there's like, what is diffusion?
Yes.
So this is our explanation of it.
Yes.
Let us know if you need further clarification on that. But hopefully you have a better understanding of diffusion. So we got Simple Rag.
Simple Rag has asked, I'm carrying out CV from higher to lower scan rates. Higher to lower. Okay. I do 2 cycles for each scan rate at, for example, 200, 150, 20, 10, 5, 4, 3, 2, and 1. Will the deposited amount reduce with cycling? I guess for deposit, I guess I don't. I've deposited 1 milligram graphene on platinum sheet to calculate specific capacity of the material. So will the deposited amount reduce with, possibly, and I guess it's more like just repeated usage in general in cycling can cause, like, there's a lot of ifs here. Like if your electrode, if it's not well bound, you have whatever, you have graphene on platinum or something.
Or if you're cycling to like a really big voltage range
Yeah.
to a degree that it's like it's stripping some of it off.
Right. Is it oxidizing?
Is it oxidizing it off?
Reducing?
That's another thing.
Are you making a bubble that causes delamination?
Mhm.
And so like, yeah, you could end up in a situation where like you find some pattern in the data, the, you know, whatever metrics you're getting from your scans. Now, obviously,
Mhm.
some of them will change with scan rate, like the double layer
Yeah.
envelope. That's just the, we just know that behavior obviously already, or like the peak height will change. You know, if you have a peak happening, from the Randall-Sevcik equation describes that. So like, there's some trends that we would expect to see no matter what changing. But if you see, for example, something you're measuring or whatever is changing in a you know, linear way or whatever, predictable way as you go, and you wouldn't expect it to, like it shouldn't or something, that could just be because, yeah, something about your sweep or the construction of your electrode is not adhering. And you can test for this, for example, if you just do the same test but mix up the order of your scan rates, right? Do the same test but do 10, 50, 2, 200, 1, you know, mix them up. You know, in theory, you should get the same results at each individual scan rate as you did when you went from fast to slow, right? And if you see a similar trend where like my whatever critical value is still changing with time that I did whatever order, then it means you're having some problem with your electrode over time, just naturally. And so, you know, you don't want to be in a situation where no matter what scan rate you picked, the last one is worse than the first one, because it's just time spent in the solution, time spent scanning, oxidizing, reducing, whatever. You don't want to be in a position where that is a variable, let's just say, right? That would be less than ideal. So so sometimes the answer to that, if you are seeing something like that, you're concerned that as time goes on with subsequent scans that you're finding the materials delaminating or whatever, you need to, it's actually more of an engineering problem than a chemistry problem, which is that you want to work on the electrode preparation, you know, find better ways to adhere the graphene to the platinum, or find better ways to make a thicker layer of your catalyst so that it doesn't fall off, or a thinner layer if you need more binder. Like, you know, there's probably a lot of trial and errors required here, but that might be the better solution than you know, than anything else, because of the electrode preparation and construction might be the critical aspect for you.
I might also usually, like when you're doing the series of scan rate studies, I would just do it again. Like, you know, our software allows us to program a sequence where you can sequence this, you know, to see whether or not I'm actually reducing, you know, the amount of stuff that's deposited. I would just perform that same sequence of experiments again. I may even do it a third time, and that way I now have triplicate sets of data in order, and I can see, hey, are the 200 millivolt per second scan rate currents or voltammograms, do they overlap on each other in like a significant way? It's okay if there's like maybe tiny deviations, but like, oh, I am actually getting less in the second one and less in the third one for each, you know, successive scan. That's another kind of easy way, because I think even if you deposit 1 milligram of graphene, if you repeated that experiment again, as Neil said, it's an engineering thing. Like, you may deposit it differently, so the voltammogram will necessarily look different from one experiment to the next. It'll still have the same features, perhaps, but there will be deviations that'll make it harder to, you know, determine that. And it's also just a lot easier to push a couple buttons again in the exact same system, to give you more data as to whether or not you are losing deposited material.
Yeah, the repetition will definitely help you isolate a little bit better whether or not any of these things are the culprit behind, you know, inconsistencies in your data or whatever. So
yeah.
Okay. we are in a rare situation getting through some saved questions. I think we should continue getting through these.
Yes.
There was a question from Asan, and they asked, could you illustrate how to determine RP from circuit fitting for corrosion studies? So yes, I can do that. But the one caveat I have basically is that, interestingly enough, while impedance is very often one of the better, if not the best, electrochemical methods for interrogating processes like capacitance and resistance, when it comes to corrosion studies and getting the polarization resistance RP, I actually do not often advocate for doing impedance compared with a very slow scan, which is what I talked about back up 45 minutes or something. And look at the timestamps. You can see we talked about like LSV at slow scan rates to get around Ecorr, right? And the reason is a little trickier, but with impedance, I think for one, it just tends to have a harder. We just talked, about Simple Rog's question with reproducibility and scanning a bunch of times and seeing if it's consistent or whatever, that kind of thing, right? All data all science and data is repetition and you running things in duplicate, triplicate, you do it over, you see if it's consistent, you see if you get the same results on a different, did it happen Tuesday? Did it happen Thursday? Like all these things are normal scientific kinds of observations and processes. And so the consistency matters, right? If you get one result once, that doesn't, even if it's good, well, you don't draw heavy conclusions if you can't reproduce it, or someone else in a different lab can't reproduce it. And so just to that point, impedance just is, as a subset of electrochemistry, suffers more than most from that difficulty in reproducibility. Now you're going to get, as I said during the previous discussion of RP and Ecorr and stuff, you will get some variation if you do RP. Like, you do it at 6 different scan rates, you might get some variation. Okay, fine. But what's uniquely difficult beyond what I just talked about impedance itself just having some difficulty with reproducibility is that you do not always get with your impedance data the features that allow you to extract RP very easily. Okay, so what do I mean by that? Well, let me draw for you. So ideally, if you're doing an experiment in a corrosion, right, and let's say you do an LPR experiment, that's like not even straight axes, it's like tilted. I can't even draw it. All right, so yeah, it was just awful. Okay, if you have E and I, it doesn't matter.
Were you going to flip the
axes? I was going to flip the axes, but it's fine. I'll just draw it this way. It doesn't matter.
At least you didn't draw the whole thing and then decide I want to flip the
axes.
That's
true, because then I'd be in big trouble.
Then it'd be a bit harder.
So this is zero current. Let's just pretend this is roughly Ecorr. I know we've had this discussion a million times as well. Let's ask us anything about Ecorr and OCP or whatever. Okay, let's just say this is Ecorr or just OCP. So let's just put, they're roughly the same anyway, for the sake of this discussion. So you have zero current at whatever, and then this is called LPR to get LPR, right? Linear polarization resistance. So this is where you just sweep the potential very, very slowly, right? A little ways away and a little ways away, right? And then basically you use Ohm's law, E equals I times R, and in this case it's RP, polarization resistance. So we just get the slope of this, right? And we can get that the slope is proportionate to R. It's either 1 over R or it's R, depending on how your axes are. Okay. Almost no matter what, you're going to get something you can take the slope of. Worst case scenario, your E versus I is like, what, crazy, like not straight, but you can still, like, I'm not saying this necessarily, like something probably went wrong if that happens. You scan too fast or your window is too big or something weird was happening. But you could even in theory still get a linear regression of even a bit of a wavy line, right? Like this isn't the best idea, but I'm just saying you could, right? In theory, do that. It's pausing. Is it going to crash? Is it going to crash?
I think you're okay.
Nope, it crashed.
It crashed.
Yep,
oh,
that's reopening. Yeah,
it's all good.
I don't need it. It's like, hey, do I have to? I don't need any of these files. Okay, hang on. Sorry about that. Let me reopen. Oh, it did
It saved it.
It saved some of my goofy sketches. It's okay. All I was drawing was some axes, so thankfully I didn't lose anything important. All right, let me bring it back up. Sorry about that. It just happens from time to time. If I it's the undo button for some reason. I just drew some lines and I tried to undo it, and it's like, nope, I don't know how to do that. You're over. In any case, almost all the time with an LPR, you have a small slope and you can get E equals IR. It's pretty easy to do. Now, what's tricky is if you do impedance. So this is LPR, right? However, for impedance, what you really need, for example, on the Nyquist plot, minus ZI and ZR, is you really need a semicircle of some kind. Now, sometimes you'll have a semicircle in that. Sometimes you'll get some weird thing, Alex, look away, where you'll have a curl. Oh God. Sometimes that happens with corrosion, which is a little bit weird. Sometimes you'll have just one thing with a curl. Sometimes what you get, unfortunately, to my point here, is you just kind of get like mostly capacitance or straight line, or it's like you would get a semicircle, but it would be like huge, like giga ohms or several mega ohms, like really, really high numbers. And that's tough. All right. And so the point here is that the polarization resistance, RP, right? RP is it's associated with the corrosion, which is a Faradaic process. And so it is a charge transfer resistance. So it's not this. It's not R0 or R ohm. It's not that. So you can't just take the leftmost intercept, like uncompensated resistance, and say that that's RP. That's not RP. RP is the width of a semicircle. But again, for all these other reasons that I talked about with impedance, and because it's unpredictable sometimes, depends on what potential you're at, right? Well, if you do this at OCP, you might not get a semicircle because you're not really doing enough corrosion. Okay, well then you pick a potential that's like 5 millivolts or 10 millivolts or 100 millivolts versus OCP. So corrosion's happening, and then maybe you'll get a semicircle. But maybe instead of a semicircle, you get some crazy looking data, because as it's corroding, the sample is just getting destroyed and the data becomes more and more inaccurate over time. And so sometimes impedance data looks like total trash, and you put a frowny face. Like, these are some of the struggles that happen with impedance when you're trying to get RP. So generally speaking, my advice is to use LPR instead. It's actually probably going to have a higher success rate. However, if you have consistency with your impedance results and you're able to get decent results and you're able to get a consistent semicircle in the mid to high frequency range, then technically speaking, the RP would just be the width of the semicircle. So if you're able to get a semicircle, like a very nice looking thing, then really what you're doing is you're just getting this width of this semicircle. That is your RP. So that would be how you would get it if you are able to an impedance. But again, take a heavy dose of caution when considering getting RP from impedance compared to LPR. That would be my advice.
Oh. Surprised you're not pushing EIS. It's just, I know, it's LPR.
It's antithetical to everything I stand for. I'm like the impedance guy here, but it's true. It's with corrosion in particular. It's oddly enough, the slow plotting DC technique is probably your best bet. It's just how it goes.
All right, let's continue. There is another question that we've had for a while and haven't answered it. We can actually catch up on some of these.
Yep.
This question from Juan Pablo 767. Could you please talk about using CV for understanding reaction mechanisms? I'm currently studying corrosion chemistry, but I'm passionate about organic synthesis and have seen a rise in the use of electrochemical methods. So you're right. Signivoltammetry can be used certainly to understand some organic chemistry reaction mechanisms. Signivoltammetry in electrochemistry is primarily used for oxidation and reduction reactions. So only oxidation and reduction reactions is where you're going to see something. But it is a way of probing the mechanism, so to say. So what I'm going to do, I want to share with you. I'm going to share we have simulation software, cyclic voltammetry simulation software called Aftermath Live. So you can see it here. And in simulation, now granted, you can of course do electrochemistry, but it's a lot easier to answer your question by showcasing this through this simulation software. So in Aftermath Live, you can select a mechanism. So when you talk about electrochemical mechanisms, we're usually talking about electron transfer steps and chemical steps. And so a simple electron transfer step involves A plus an electron going to B, and there's some kind of equilibrium that's associated with it. You could also have it be an oxidation. I can toggle it so that A loses an electron and produces B. And with each electron transfer step, you have an oxidation reduction potential associated with it. You have a kinetic rate constant associated with it. And you have this alpha, which is referred to as the transfer coefficient, which describes the like symmetry of the transition state barrier going from your oxidized to reduced species. And each species, A and B, also has a concentration and a diffusion coefficient associated with it. And so even, we can just kind of autofill this. We can also autofill the cyclic voltammetry parameters. So experimentally, regardless of what the mechanism is, you have parameters within a cyclic voltammogram that you can adjust the number of segments, the initial potential, the final potential, the upper and lower limits, and how fast you scan the potential. The sweep rate is actually one of the most important parameters that you have as an experimentalist when it comes to probing a reaction mechanism. So actually, we'll just open these things up. And then, of course, there are other more specific things in simulation, such as the nature of diffusion, the double layer capacitance, and the uncompensated solution resistance. This is actually better for, I would almost say, teaching purposes. But when you simulate this, you can get these nice voltammograms. You can then learn and understand like what is actually happening while you're doing a CV, cycling the potential, and looking at the concentration versus time profile, as well as the surface concentration. So the distance from the electrode, the concentration profile as a function of the distance from the electrode. How does that change during a cyclic voltammogram? Now, this is very easy for something like a basic, just a basic one electron redox reaction. But you'll quickly find that this will get much more complicated and complex when you start adding chemical steps. And so, for example, if you were to add a chemical reaction, you would then have to specify, say, maybe B just chemically converts to some molecule C, and there's a forward and reverse rate constant associated with that process. Let's just say it was 10 and 10. There's actually no change. And let's just say the diffusion coefficient's also the same. And then this also has, there's none of this in the beginning. But you'll actually find that when you simulate such a voltammogram, you actually will start to generate a slightly different concentration profile. You'll actually start to generate some C in your reaction as a function of time. And even though your general concentration profile will look different with C, with this chemical step, than without it. So this is just kind of the baseline. As I could spend hours, if you will, just going over like, oh, if I change the rate constant, how fast does this electron transfer process occur? I would get a very different kind of voltammogram. You'll even notice the voltammogram is kind of elongated, sort of say. The peak separation is different between them, and as such, even the concentration profiles is kind of the same by the end of the voltammogram. Surface concentration profile is similar, but the shape of the voltammogram will start to be different. Additionally, if you start to make, say, the reverse rate constant, or the forward rate constant faster, you'll also start to see differences in the shape of the voltammogram. It'll actually begin to look more and more irreversible over time. Like, oh, I'm actually not gaining as much on the reverse wave because of the rate constant associated with this chemical step. And this is just for like an electron transfer plus a chemical step. There are many, many different types of reactions, and you can actually create your own electrochemical reaction. You could even have two chemical steps before an electron transfer. You can have an electron transfer step followed by a chemical step, followed by another electron transfer step. You can design your own. And all of these things that help us learn more about the mechanism can be learned. You usually do need to use some level of simulation software to actually start to deconvolute and figure out what are some of these things. And I guess my last plug, if you will, or last thing to mention is that the scan rate will be something that will help you study these things. So if you are doing stuff in an organic chemistry lab or even a corrosion lab, I'm going to archive this voltammogram quickly, and I'm actually just going to change the scan rate a lot. And let's say I'm just going to simulate it. You'll notice that the voltammogram looks very different now. And if I overlap the voltammogram that I just had, so if I go to voltammogram, I can pin this guy so that I can see the overlap voltammogram. You'll notice, oh, when I go to such very large scan rates, I actually get a different kind of voltammogram. And if I start to adjust it, if I change the scan rate, I'll start to see a lot of differences, if you will, between them. And I can start to kind of test and play around with the scan rate experimentally. Helps me learn more and more about how the shape of the voltammogram goes. The fact that this back step didn't change as much as the forward step when I changed the scan rate between 150 millivolts per second tells me some information about the fact that this chemical step here is actually very fast. And it's like, oh, if these things were equal, for example, I think my result would also be different from. It's like, oh, it shows up here. Oh, so these, these are now more equal. The forward and the reverse rate between A and C are actually equal, as opposed to when one is 2 times 100 times faster than the other one. So that is, I think, my kind of brief showcasing of the simulation software and how you can use electrochemistry to study electrochemical mechanisms, even potentially even some like organic chemistry mechanisms. But really, it does need to have an electron transfer step for you to kind of simulate and showcase this. So so hopefully that was helpful. That kind of answered the question.
Mm-hmm. And we're on a roll, so I'm going to get the last one.
Yes.
Here. So if there aren't any other questions, we will probably wrap up a little early today, which is fine. But type any questions you have into the chat in the next little bit here, and we'll get to them. Mm-hmm. But otherwise, I'll answer this question, and then we might call it a day, I suppose. But Ziba had asked a question some time ago. So again, apologies if we didn't quite get to this in a while. It's a fun problem to have. There's a lot of engagement from people, as we say. But they asked, why is it preferred to change from time domain to frequency domain? What is the reason or importance? So this is an impedance question. I'm not going to destroy impedance like I just did, apparently. But honestly, the way I want to answer this is that it's a very beginning of the first part of my 5-part EIS webinar series. I talk about impedance as a technique, why it's important, and the answer to why it's important on the most general way that I could answer that question is an answer to this question, which is that why would we switch from time to frequency domain? And so let me just go through those slides, and that might be a good sort of way to answer this question. So the way that I like to, again, sort of bring this up, as far as impedance specifically, is to compare electrochemistry to a symphony, like a symphony orchestra. And so in a symphony, in a large band, and for those of you who are young, you don't know what a symphony is. So you have to bear with me here. But there used to be music that was made not by computers. I know it's hard to believe, but this used to be done with people and strings and hands and all kinds and mouths and all sorts of weird things, are, old style things. And we made music, beautiful pieces of music. And you'd sit there and listen to it for more than 19 seconds and you would enjoy it. And that's how life used to be like 200 years ago. So, okay. So the point is, if you imagine an orchestra or a band or a symphony playing some piece of music, there's a lot of instruments that are playing at the exact same time. And when you're listening to this, your ear takes all of it in at the same time, right? You hear the violins playing their part, you hear the French horn, you hear the cello or the upright bass, and you hear the marimba playing its part. You hear it all at the same time. It makes this beautiful piece of music come to life and hear it. But it sort of naturally begs the question, especially for those of you who might be musical or have been in an orchestra or a band. I have, so that's why it's natural for me to kind of use this as an example. A logical question might be, okay, well, I'm hearing all of these instruments, but what happens if I want to just hear one at a time, right? That would be a process that we would sort of call deconvolution, right? I'm deconvolute, break down into its component parts this piece of music. And, you can imagine why you might want to do that. For example, if you're the conductor of this orchestra and you want to improve the band's performance or the orchestra's performance, you might want to make sure that the violins are playing their part correctly. You might want to make sure that the percussionists are playing their part correctly. So, well, if you're the conductor, you can stop the whole group, tell the violins to play at measure 16, and then you get to hear what you want. But practically, we can't really do that, right? And so in the same way that an orchestra or a piece of music has a lot of different instruments playing at the exact same time, blending together, with an electrochemistry experiment, we have a similar phenomenon happening. We have a lot of processes that are happening at the same time. They're just not musical. Okay. And so the point that I'm making here is that impedance, and this will get to the time versus frequency domain, impedance is like a really good ear that can deconvolute each of these instruments. And so I'll explain. So when you have a potentiostat and a cell and you're doing electrochemistry, it's happening in time. Everything is happening in time. We live on Earth. There's time. Okay. And so you're doing some experiment, DC electrochemistry, right? Cyclophotometry, chronoamperometry, whatever. You are measuring or monitoring potential and current over time. And there's processes that are happening at the same time. There's charge transfer resistance, there's double layer capacitance, there's inductance, there's mass transport, there's diffusion, electrical double layer, right? All of these things are occurring at the same time in your experiment, right? And we know this, right? When we do CV, we scan and we have a gap between the oxidation and reduction scan, and that's related to the double layer capacitance. And then, that capacitance is still happening, even though we have a peak. That's also a charge transfer process, and there's some resistance associated with that. And then there's, diffusional effects that take place when the peak decays, right? Cottrell equation kind of response. You have the diffusion layer grows, and so your current decays. And so all of these processes are happening at the same time. The key, however, is that they are happening at different speeds. They're happening at different rates. So the charge transfer resistance, or the Faraday process, happens at some speed that's, associated with its kinetics, right? Could be fast, could be slow. A lot of times it's relatively fast. As Alex just kind of played with the simulation software and showed you, the K values, or it could be really, really fast or really, really slow. So generally speaking, let's just say it's relatively quick. Double layer capacitance, it sets up quite fast, but you might the way it probes. I'm not sure if it's basically because a capacitor is inversely related to frequency. Its impedance grows as you slow down your scan, and so that effect can be a little bit of a slower one, where you measure its effect. Inductive effects in the cable happen very, very, very quickly. And then diffusion is like the slowest process. That's like over long periods of time, the diffusion layer grows and the current decays. So these are all happening at the same exact time, but they are happening at different rates of speed. That's where the frequency domain comes into play, because frequency is the inverse of time. And so faster frequency corresponds with faster processes, and slower frequency slower processes. And so what we can do is turn our experiment from the time domain into the frequency domain. Now it's still happening in time, but what we're doing is modulating with the AC waveforms different frequencies of our signal. And so we can probe very, very, very quickly to get things to be on par with things like the inductance or maybe some charge transfer processes or uncompensated resistance or whatever. And then we can slow it down and modulate the signal to be very, very slow to capture some of those slower processes like the diffusional effects and things like that. And so what that sort of does for you in the context of impedance for any electrochemical experiments is it's like hearing one instrument at a time in that symphony. And so that's like probing one of these resistors or capacitors or one set of resistor capacitor process at a time. You know, the way that these processes double their capacitance and charge trans resistance, whether there's one or two of those or four or five, or whatever, they make, you know, they relate to each other in complex ways, like some of these example circuits. You know, there's a variety of analog circuits where these you know processes relate to each other basically. And so by changing the frequency of my signal, I can probe individually those kinds of processes in a way that is not often very possible with DC electrochemistry, because the speed, you know, you can change the speed a little by like modulating scan rate. There's some ability with DC electrochemistry to modulate speed, but not as effectively as you can modulate speed with a frequency AC signal with impedance. Okay. And so that's sort of that answer there, as best I can say, which is why would I change to the frequency domain? It's because I'm able to probe different processes that are happening at different speeds, different rates, in a way that DC electrochemistry doesn't often afford me the ability to do.
Also, if you're looking at like a sine wave on the time scale, it just looks like it's a wave. And then you have another one that's a wave.
Mm-hmm.
And they have another one that's just a wave. And like if I look at just a bunch of waves, it's very hard to figure out what's going on. But if I convert all those waves from the time to the frequency domain, they become a peak. They become like a solid line.
Yep.
And it's like, oh, well, I can see that. I can see that like very clearly. It's just one line. It's not like, you know, a dozen of these squiggly lines that I'm trying to like interpret data from. It's much more easy to like understand what's happening that way. But that's just another thing.
Yes.
Well, it doesn't look like we have any more questions. Before we wrap up, I do want to make a quick plug. We are doing we host a bunch of workshops, you know, kind of electrochemistry workshops. An upcoming electrochemistry
not
workshop.
mountain biking workshops.
Not what?
Mountain biking workshops.
Not mountain biking workshops.
Oh, they're electrochemistry workshops.
Electrochemistry workshops.
Yeah, that's good.
An upcoming workshop we have is the Pine Villanova CV boot camp. That's going to be this June. If you're interested in signing up, you get to learn about all these things and get some hands-on experience doing signal voltammetry and IR compensation, spectroelectrochemistry, and just like earlier, you know, I think we mentioned this a while ago, but we have this new website that we developed, and it has all these new tools, reference electrode conversions, learn about webinars, workshops that are upcoming, things like that. So I would also recommend that you check out the Pine Research website as well for lots of things, and we'll talk about it on the live stream, as it can actually be very valuable and helpful when you're trying to figure out how to do certain things.
Yeah. Plus, you get to meet Alex in person.
Yes.
And then you can ask him anything about electrochemistry, and he can't escape.
Yeah.
Because right now we can just escape because
we can choose whose questions we want to ask.
We're on the internet.
Yeah.
And it's escapable. But in person, he'll have to answer all your questions and stand there for hours just answering all of your questions.
Yes. So come to Villanova and just make me not go anywhere. That's right. I would just stay there answering questions all day.
That's correct. Even questions about mountain biking, because it's not a mountain biking workshop. but it
Yeah,
could be if you want to make it.
It could be. I don't know that much about mountain bike. I used to. I wouldn't even say I did very much mountain biking. I rode a mountain bike sometimes in wooded areas, but I wouldn't even say it's like real.
I only ever used a
mountain
bike
bike.
to get to class,
And that's it.
and that was it. I've always hated bicycles. It's not my favorite form of exercise or transportation. But I lived off campus for a couple of years, and it was the best way to get to class, even in the snow.
Yeah.
Which was very fun, not falling and getting a concussion every time I was trying to go to my chemical engineering classes. So,
oh God.
Yeah, that takes me back. But anyway, I think we will call it there for the week. A little bit early. I'm glad actually we kind of got to get through some of these questions. That, if folks do see them, know that we see your questions and we just wait. It's been like
several,
3 months maybe.
Plus. Yeah.
For us to sometimes get to some of these questions that we've had cataloged, we want to kind of get to, and it's one of those things. It's hard to get to sometimes with a lot of live questions, which we appreciate. So with that, we will wrap it up. I think some people it's Easter this weekend.
Yes, that's right.
There's a lot of folks around that have these days off. So anyway, I'm guessing that's why there's a little bit of a chill week.
It varies.
Which is
it's hard to know sometimes, but yes.
Anyway, we appreciate everybody, and we hope everybody has a great weekend and great week ahead, and we will see you next week.
All right. Bye.
Bye.